Welcome to the start of Regenerative Metropolis. I am David Lewis. I am the Dean of the School of Constructed Environments at Parsons. I am also a principal of LPL Architects, and I am also the proud co-author of a new book called Manual of Biogenic House Sections that's just out. So as educator, architect, and plant-based building advocate, I greet you today. This symposium, tackling the critical but not always aligned intersection of embodied carbon, operational carbon, and the human health consequences of our material, engineering, and design decisions falls intentionally on Friday of Climate Week, in the heart of the global metropolis and within the space of education and change. I want to begin by acknowledging the incredible work of New York Passive House and the inspiration provided by Healthy Materials Lab at Parsons for their partnership in today's endeavor. To situate you, for those of you less familiar with Parsons, a few key facts. 6,000 students and over 1,000 faculty, 5 schools, of which the School of Constructed Environments at Parsons has 780 of those students and 160 plus faculty, intertwining the study of architecture, interior design, product and industrial design, and lighting design in 10 programs at the undergraduate and graduate level. I highlight the cross-disciplinary nature of this school precisely because it is the capacity to speak and understand between disciplines, between knowledge areas, that is necessary to address the fundamental and deep-rooted transformations that must happen to move beyond the linear practices inherited from the Industrial Revolution to fully embrace regenerative and circular ways of thinking that our future demands. We do indeed, though, have an opportunity to restructure and reimagine our metropolises as carbon banks and urban mines using biogenic and geogenic materials designed for disassembly to meet the sheer scale and incredibly tight timeline of mitigating global warming while equally cultivating biodiversity. But to do so upends singular practices and addresses thorny questions caught at the intersection between. Essentially, this gathering of all of you, experts, students, faculty, designers, manufacturers, and engineers, asks you to think holistically, questioning the pursuit of isolated performance and aesthetic goals. Let me give you an obvious example to demonstrate this point, one that will be familiar to many of you. While conventional polyurethane and spray foam insulation may indeed be high-performing and exceed operational energy standards and fall within current New York City building codes, are we simply not moving the carbon emissions from operational to embodied, while simultaneously burdening the earth and frontline communities in particular with the depositories of its genesis? Weight especially needs to be given in answering this question to climate justice and the long-term health consequences of our material and design choices. And they must figure prominently in framing those shared opportunities that we will explore this afternoon. To set this frame, I'm very pleased to be able to introduce Allison Mears, the co-founder and director of the Healthy Materials Lab at Parsons, a practicing architect, scholar, researcher, and faculty member of the School of Constructed Environments. Allison is a leading voice in advocating for transparency and in bringing the impact of chemicals to the forefront of this equation. Recognizing the importance of her work, Allison received in 2022 the Women in Architecture Innovators Award from Architectural Record, an award shared with co-founder John Sawyer Ruth, and their collaborative work at the Healthy Materials Lab was cited by Metropolis magazine as redefining sustainable design. I welcome you all this afternoon, and please join with me in welcoming Allison Mears.
Advancing, Andreas. Beautiful. Thank you. Thank you for that lovely introduction and welcome this afternoon to this great event. I'm going to talk a little bit, as David said, about toxicity and embodied carbon and the relationship between those things and all of us, our health and the planet's health. In the last few years, we've witnessed incredible change, global, cultural, and environmental rifts, including a pandemic and catastrophic climate events. We understand that there are immense problems, and we commit to act wisely, urgently, and immediately, because we know we're all connected across this amazing planet. We ask the question, what if we changed our architectural and design practices to construct a new future? Fossil fuel refining products produce both the toxic ingredients for the products we use and the toxic emissions that pollute our planet and ourselves in all our buildings. We know that manufacturing generates greenhouse gases and pollution. We need to change the way we use fossil fuels to make a truly just transition for everyone to green economies. At HMO, we address the toxics and climate issue by charting pathways to make it easier for all of us to design and build healthy buildings today and accelerate that rate of change. Our work begins with common building materials that often contain toxic chemicals. Many people are unaware of this issue. When we specify products as architects and designers, those choices can include chemicals like flame retardants, fluorinated stain treatments, formaldehyde, a range of plastics, and a host of other chemicals that are problematic. And as these chemicals break down as they do, nothing is stable. Chemicals can be released and harm those living in the space. We do know what's inside of food products because ingredients are regulated by the Food and Drug Administration. And many people look at those ingredients. They do, particularly if they eat Doritos. We assume that materials and products that we buy, but there are no regulations, surprisingly, for building products. Many people don't know to ask for product ingredients. Surprising. Food, buildings, very similar. We assume that materials in the products we buy have been tested for safety. But most, if not almost all the chemicals commonly used in building and consumer products in the United States are not regulated for their impact on human health or the environment. Only 250 of the more than 86,000 chemicals currently in use are tested, and only 5, those 5 on the bottom there, which we all recognize as being problematic, have been partially restricted by law. These chemicals have a profound and negative impact on both human health and the planet. The materials used in buildings, cities, objects, and furniture are releasing toxic particles that are absorbed into all our bodies. We are truly, if we are what we eat, we are where we live. Research shows that the petrochemicals used to make building materials have a high carbon footprint. Fossil fuels are used to power the factories, to make the ingredients, and to transport the products and raw materials. We need a new set of guidelines, policies, and regulations to help us make transitions to building better. We can build for a new future if we create viable, marketable products that are affordable, if we integrate and transform existing structures, if we build healthy, affordable places for everyone, if we support resilient and regenerative systems, and we design with new nature-based practices. Our theory of change is to empower and enable architects and designers to make change today. We offer a wide range of resources to make this possible, including a range of educational programming. On HMO's website, we provide free access to carefully vetted collections of healthier materials and offer physical material examples in our New York City library on campus. And we share material health information widely. If you're interested, sign up to learn more about our public events in person and online. As you move through the presentations this afternoon, you'll see a whole range of responses to these questions that I've just posed and that David has highlighted. We ask that you also remember that toxic pollution in all its forms is a persistent problem. It's evident that there is a clear relationship between toxic chemicals and embodied carbon content. No one would want to design a high-performance, energy-efficient building that was built with toxic materials. It is possible to build better and reduce both toxic and carbon emissions. This is better for all of us and better for the planet. I'm looking forward to this afternoon's presentations, and I'm inspired by the work of this community. I'd like to introduce Andreas Benzing, my esteemed colleague, who will introduce this afternoon's program. Thanks, Andreas.
Thank you, everyone. My name is Andreas Benzing. I'm an architect, teacher, and executive director of New Passive House. I would like to welcome you all on behalf of New Passive House. I would also like to thank NYSERDA for sponsoring today's event. NYSERDA is a very strong partner in decarbonizing this construction environment here in New York State. So thanks for your support. I also would like to thank our team, Alison Mears, Lena, Sarah Bayer, David Lewis, and Buck Moorhead, and all the volunteers who pulled off today's event. We are very excited and thankful for the collaboration with Parsons School of Design, because it allows us to bring academia and also the building industry closer together, while bridging the divide between architecture and technology. I would like to quote Rainer Benham from his book, The Architecture of the Well-Tempered Environment. The idea that architecture belongs in one place and technology in another is comparatively new in history, and its effect on architecture, which should be the most complete of the arts of mankind, has been crippling. He wrote that in 1969. Many of the climate risks we now face are related to the fact that architecture has abandoned to a certain extent responsibility of a climate controlling enclosure design, while advances in MEP technologies were placed mostly with engineers. High-performance passive house efficiency brings back the idea of integrating power-operated and structural solutions in architecture. It is a powerful tool to remove the separation between embodied and operational carbon thinking to reimagine a truly regenerative metropolis. I would like to welcome Sarah Bayer to introduce today's symposium and program. Sarah is Director of Sustainability at Magnuson Architecture and Planning and is a Director of the Board at New York Passive House. Thank you.
Good afternoon, everyone. So glad to see you all here. I'd like to share with you some more details about the origin of the symposium's title, Regenerative Metropolis. Our collective work towards a more sustainable city and addressing our greenhouse gas impact has been impressive in many ways thus far. Keeping in mind all that we still wish our city to be, we are embracing heat pumps, steering our energy code towards a more sensible balance of enclosure robustness and mechanical system sizes. We've improved our stormwater requirements recently. Birds are protected from hazardous collisions with our buildings. All of our lights are changing to LED. We are tracking our energy use and mandating improvements and transitioning our grid to be 100% renewable. We are more justly allocating resources towards traditionally underserved communities and are about to divert all of our organic waste towards higher uses than the landfill. It's important to appreciate what is possible today that was only a dream yesterday. Sorry, it was a dream yesterday. If only to give us honest hope that we can achieve our next dreams. So far, the narrative for this stewardship has been focused on sustainability as a catch-all for increasing efficiency and doing a little less damage to our natural resources in order to make sure our children have as much as we do now. But what we have now is damaging to our health, physical and mental, reduces the nutritional value of our food, and destabilizes ecosystems we need to survive. Our collective minds, therefore, have been shifting the narrative towards a new vision, that of regeneration. This means that humanity can actually improve upon the world, that we can intentionally increase life and its abundance, and also repair damage we have already done. Think of a permaculture farm as an example where the nutrient content of the soil increases year after year, and the amount of life is astoundingly diverse and abundant. In the context of a city, this means that we can store carbon in our buildings with emerging technologies, which we'll talk about today. It means that we can create circular paths where nothing is thrown somewhere else for someone else to deal with. It means we can build high-performance architecture that uses very little energy. Passive House's focus on airtightness is the biggest bang for our buck and has matured significantly enough for it to be embraced on a metropolis-wide scale. We, in fact, have more agency to choose this path than we realize. We now have the technology and deeper understanding to know that we don't have to choose prosperity over health. We can have both. When plastics were emerging in the world, there was great optimism to the prosperity they would bring. We deserve to have the same optimism today. Because of countless human lifetimes of passionate inquiry, we more deeply understand the systems in the natural world and our impact on it, and just how many other choices we have to polluting technologies. It's easy to recognize that so many of our objects in modern day society are made from polluting fuel and material sources, and we are told that we have to give up that way of life if we want healthier options. This is not the case. The problem is, we have spent so many years going down a particular line of scientific inquiry, that of petroleum chemistry, that we have ignored other options. The Passive House Board and Conference Committee invite you to envision in detail the regenerative, abundant metropolis that we can create. As Theodore Hook said in 1840, the best way to predict the future is to invent it. After our keynote speaker, who Andreas will introduce, the first session is focused on low carbon, circular, and carbon sequestering materials. Then we'll have a short break, continue to a session focused on mechanical systems' role in both passive house level energy efficiency and embodied carbon in building systems. Following this will be a panel discussion and presentation on policy at multiple levels. We are looking forward to a collaborative and inspiring discussion, which is humanity's true way of getting things done.
So it's my great honor to introduce today's keynote speaker, Felix Heisel. Felix is a licensed architect in Germany and partner of 2HS Architects and Engineers, an office specializing in the development of circular prototype typologies. Felix is an assistant professor and director of the Circular Construction Lab at Cornell University's College of Architecture, Art, and Planning. He is a faculty fellow at the Cornell Atkinson Center for Sustainability and the graduate field member in architecture systems engineering and meta design computation. Felix's scholarship focuses on the systemic redesign of the built environment as a material depot of endless use and reconfiguration. He has received many awards for his work and published several books and articles on that topic, which are also on display in the lobby area. So it's my great pleasure to welcome Felix to the podium.
Good afternoon. Thank you, everyone, for the invitation, especially Andreas and David for making this possible. As mentioned, my name is Felix Heisel, and I'm here sort of representing both of these two hats that were just mentioned. On the one side, I'm going to show some projects in the office, and then I'm going to show projects from the research, the ongoing research at Cornell University. I'll fly through quite a few scales from the material to policy, hoping to kind of set up maybe some of these or induce some thought into some of these panels that Sarah just mentioned for the rest of the afternoon. Climate Week is traditionally also a moment where many reports are being published. I haven't had the chance to go through most of them yet, but is it closer? Okay. I hope you can hear me. Otherwise, make a sign, I'll speak up. This is just one of them, one of these new reports that came out 3 days ago about the fact that we're now measured all 9 of the planetary boundaries, and we're actually exceeding 6 of these 9. So it's a dire moment in time that is summarized in this paper by Earth is now well outside of the safe operating space for humanity. To understand that and to understand the scale of such a sentence, it helps me usually to look a little bit, or actually quite a lot, into the past. This is the geological timescales, and you can see at the very top this thin sliver that is being pushed in there, which is called the Anthropocene. But if you look at the past 800,000 years, then what is called the Milankovitch cycles dominated the climate on our planet. So the eccentricity, the obliquity, and the precession in the relationship between the sun and the planet Earth. And these are cycles, these sinus curves that you can see at the bottom of the screen are cycles that have a range between 40,000 and 200,000 years. And if you overlay these different sinus curves, you get that green curve that you can see at the top of the screen, and underneath you see measurements from ice core drillings that went down in Antarctica for 3,000 kilometers, and so we can reconstitute basically the climate over the last 800,000 years and see that ice ages, for example, correlated with these peaks in these Milankovitch cycles, saying that for the last 800,000 years, the climate was dominated by planetary scales. Now come the last 70 years, where we see indicators of human influence, and these are all eerily similar. They all start picking up in the 1950s. They all go exponentially up. Some fortunately have slowed down. Some are still on the rise, but it doesn't really matter what we're looking at. Dam construction, water use, GDP growth, population growth, all of these graphs are similar. And this is the reason why we're now talking about the Anthropocene, right? Where human influence took over planetary scales. And I think it's important for us to understand that scale. And then the question is, what does all of that have to do with the built environment? And so these are 2 more of these graphs that again look the same, right? In the 50s, we're starting to rise exponentially. Here you can see in magenta material, building material extraction on the left, globally, total extraction, and on the right per capita, so that we can't say, well, we're more people on the planet, of course we need more materials. No, every one of us is needing more material, and we're sort of all part of this that's happening, right? And so if we sum that all up, estimates say that the built environment, if you take a building from the very beginning till the very end of the building's lifetime, are responsible for more than 50% of materials that are taken out of the Earth's crust, more than 40% of solid waste that is being produced, and more than or about 40% of the carbon emissions that are being emitted. And so this is sort of the starting point. But now what can we do about it, right? And so these are charts by Architecture 2030, kind of figuring out what would it take for the built environment to stay within the Paris goal agreement to restrict global warming to 1.5 or below 2 degrees of global warming. And the estimate, this is from 2020, so now 3 years ago, was that we need to reduce our carbon emissions by 65% in the next 7 years to stay within these limits. The unfortunate news is that, at least in Germany, we have just announced that this year, because of that record summer that we've had, we actually reached the 1.5 degree already. This hasn't really been discussed in US news yet, and I don't know where we are exactly, but we're we're damn close to this, right? So we need rapid action. And this is where it gets interesting in terms of a relationship between embodied and operational carbon. So what you see here are these 39% that I'm sure all of you have seen before. This is a global number in the relationship between the emissions that come out of building operation and the construction of buildings. But if you take one building and you construct it today, and you think about the timeline, these 7 years or 5 years that I just mentioned, these ratios shift dramatically because, of course, embodied carbon emissions are emitted on day one of a building's opening, right? All these emissions have been emitted, versus the operational carbon emissions are emitted little by little over the next 50 years in this scenario. And so if we only have 7 years, then suddenly the way we built becomes really interesting as a starting point for the conversation. Additionally to that, of course, and you're all experts of that, our buildings are getting better and better in terms of the percentage between embodied carbon and operational carbon. So the more passive a house, the more important the way we built it. And then the question, what do we do with that now, right? And so we know that different materials emit have different embodied carbon emissions attached to it, but maybe more important is that strategy pyramid on the right, where a material that is already here, right? And we start reusing that as a strategy, that has the least emissions attached to it, because these emissions have been already emitted and we're starting to preserve those. And so adaptive reuse, building preservation, reuse, and deconstruction are strategies that we're really interested in. And so the Circular Construction Lab really focuses on this shift from a linear economy to a circular economy, where we shift from take, make, throw to take, make, repeat, with two different focus points. One is looking into the past, trying to understand the built environment as a resource for future construction, trying to figure out what do we need to know about the built environment to actually activate it as a resource, because we usually don't even know what is in our buildings. What kind of strategies of extraction can we implement? What kind of economic business models are attached to that? What kind of social constructs are attached to that? And on the other hand, looking forward, it's the question, how do we now, knowing all of this, design differently so that buildings that are built today don't run into the same problems in 30, 50, 70, hopefully 500 years down the road when they get to the end of their use time. And just because sometimes we're being asked, so what is a circular economy? The definition that we're using is one that is published by the Ellen MacArthur Foundation and kind of repeatedly overhauled over the last years. And so a circular economy is one that aims to eliminate waste and pollution, circulate products and materials at the highest utility and value, and regenerate nature. So the projects that I want to show address these two directions that I just mentioned. I'm going to start with the question, what do we do with the built environment as it is, and how can we see that as a resource? This is a pavilion that we built for the Ministry of Environment in Germany in 2019. It's called the Mehrwert Pavilion, and it's a structure that is entirely built of secondary materials. So there's no virgin resources in this construction. And I'm pointing it out mainly because of the story that we've had to look at in the reuse of steel. But we've had 4 different material families in this building. The facade is basically only recycled glass. Then we have all the furniture that is recycled plastics. It's actually recycled household plastics in this case. And then we have reused and recycled mineral waste for all the flooring and the foundation. And so this is an image of these foundations. For example, that white snow-like material is ceramic waste that otherwise would have been landfilled, and we found a way to kind of define the sieve curve through milling it in very different particle sizes to actually form, without any adhesive, a layer that sustains 6 million visitors over 3-4 months. And so we kept this material out of the landfill. We didn't add anything to it. And we created actually a wonderful aesthetic because it sparkles in the sun like snow. It was incredibly beautiful. The facade is using secondary glass resources, but basically brought into a ceramic product, a glass ceramic product. And the interesting thing is that it keeps the aesthetic of the shard, right? We're not melting this material all the way to the melting point, but it's just soft enough to create a new product out of it. So we're using less energy, but we're also keeping that shard, which gives the aesthetic of something that you could never generate from a virgin resource, and is really talking about the history of the material. But what I wanted to mention most about this project is the reuse of steel. We can always recycle steel, but what we wanted to do here is reuse it directly. And so the steel comes from this coal-fired power plant, which is another little anecdote because we're now shifting to renewable energies. And so we're shutting down coal-fired power plants, huge infrastructure buildings, and we actually don't know what to do with them. Unfortunately, Germany's solution to this building was to blow it up, which is questionable as an answer in this larger conversation about shift to two different energy sources. But we were able to take that steel that we needed for this building out of this power plant before they blew it up. The problem was we had no idea what steel we got, right? Because there was no documentation, it was not stamped. And so the office needed to go out and say, well, we need to do 5 tests at a large sample size, chemical composition, weldability, tensile test, compression test, to figure out in the end, yes, this is standard structural steel. And with that knowledge and that stamp, we were then able to get a building permit for this. And the reason why this is important, I think we'll get back at a later stage of this talk. The documentation of our built environment is an increasingly important part in the transition to the circular economy. The point that I wanted to make with this image is that, of course, there's a design conversation about this as well, because we started with a building stock that is non-uniform, that would have never resulted in an image like this if we would have started with standard steel that we're getting from, I don't know, a department store, and so the dimensions, the sizes, the condition, the marks, the historic marks, right, determined the design process of this pavilion. Now, this is one example from Germany. If we want to scale this and if we want to translate that into a US context, this next project is a deconstruction project in Ithaca, New York. And so here we had a developer that got a permit to take down 11 residential houses from 1906. And you see that process. So the excavator is driving through those houses. Essentially, it takes 2 days to take down that house. Everything is, driven over, made as small as possible. One stream the recycling, put everything into a dumpster and shipped off to the landfill. We convinced that developer that we could deconstruct one of these 11 houses as a sort of an academic exercise next to the 10 that were being demolished at the same time, under the condition that we don't cost him more than the demolition would cost him, and that we're not delaying his demolition, which meant we needed to be out of the way by the time the excavator ate the other 10 buildings. Which was a challenge because a deconstruction is more expensive and it is more time intensive than a demolition. And so what we needed to do is develop a new process of deconstruction, which we are calling panelized deconstruction. We work together with the Building Deconstruction Institute out of Seattle. And essentially the idea is to cut a building into pieces that are as large as possible so that they still fit on a flatbed truck to be then shipped, basically trucked away from the site as quickly as possible to do the time-intensive deconstruction of these units or components in a controlled environment in a warehouse at a different location, which meant that in this case, after 4.5 days, we had the site cleared. It was a 3-story, 13-bedroom residential unit, which took us 4.5 days to deconstruct. We had a very happy client because we were out in time. And we had a large amount of data that we are now sieving through since a year to sort of create a narrative about deconstruction versus demolition. And so why are we interested in this? One part is that it is an insanely positive community engagement tool. And so we had the acting mayor of Ithaca carrying out floorboards of these houses to rescue wood from the demolition, which was a really important way to start a political conversation about what we're doing in the built environment. We used it as a capacity building program with local trades. In this case here, you see Trade Design Build as sort of one of our main contractors, getting a training by the Deconstruction Institute to pass this knowledge into the industry. We've worked together with the apprenticeship program of the local union to bring the apprentices into this program and sort of start training them in deconstruction. And we're bringing in students. This is my design studio class that is working on denailing and deconstructing timber. And it's a really interesting exercise for an architecture student to take down a building and especially take down a detail that wasn't meant to be taken apart, because you spend 2 hours trying to save this timber beam, and in the end, it might still snap because that last nail just didn't give way, and there's a lot of frustration involved. But the benefit is that when you go back to your drafting table at the end, you're never going to draw a detail like that you tried to deconstruct, right? You're going to draw something that is reversible, and that is meant to be designed for disassembly, because you've in your own hands sort of experienced the frustration of taking something apart that isn't meant to be taken apart. A bit more scientific is a real analysis of these two case studies. And so now we're seeing in the local environment in Ithaca that we're actually not only much better for the environment, but we're also cost competitive. Because the revenue that we're getting from the resale of these materials that we took out of the building actually offset the additional labor costs that we had for deconstructing that building. And this is really good news, because if we're cost competitive, we can shift the conversation to the things that actually matter. The embodied carbon that we're taking out of the building, the additional labor that we're creating, the green workforce development, the new jobs, the cultural heritage that's being preserved through deconstruction. All of this is what we actually really want to be talking about. We don't want to talk about the costs. And so this shows we can have that meaningful conversation. The other thing that I mentioned in the very beginning is we use this project as a starting point to understand what is in a building. And so what I'm showing here is what we're calling a salvage and deconstruction survey toolkit, which is essentially a set of tools that we're developing and continue developing on scanning the built environment. On the right side, you see a LiDAR scan of a building. On the left side, you see an Excel survey that we're started to create, but we can link these two. And so within and of course that LiDAR scan has the benefit that it is embedded textures and photographs. And so when you connect these two components, you get a rather quick estimate of material contents of a building. It took us two hours to scan this house and a couple hours post-processing, but you then know, of course, as a ballpark figure, what is in the building, what kind of details do you expect in that building. We're using construction archetypes that we're linking to these surfaces. And we're not necessarily saying, well, you want to use that to then sell exactly 3,742 kilograms of timber, but we're using it to start a meaningful conversation with a deconstruction expert, with the policy on getting a deconstruction permit. And so all of these numbers help to have a more informed conversation with local stakeholders about a specific building and the benefits of saving it. Here you can see these a set of these construction archetypes that were developed. These of course is a local database, and we're really interested in expanding that so that this tool is more accurate in different locations. But this is a ongoing research project. And here you can see sort of a quick summary of what is possible to get out of this scan very quickly. One is, of course, an embodied carbon number. You get surface areas, you get different types of material information. Now, we can do this, we can, of course, do that on the building level, but I think it gets really interesting when you get this data on an urban scale, because while we can, of course, take materials out of one building to build one more building, it's unlikely that this will ever be a direct move. It's more likely that we'll take materials out of one building and bring that into 10 buildings, and we're taking other 10 buildings and bring material into one. And so we're talking about an urban marketplace, urban stock flow model. And so we need to know a much better understanding of that so-called urban mine. Now, interestingly, Ithaca is a fantastic case study for us to do this, because in 2019, the Ithaca Common Council approved what is called the Ithaca Green New Deal, which is the plan to decarbonize the entire city, so all 6,000 buildings by 2030. It's an incredibly ambitious program, and it's been over the news left and right and everywhere. The main component is a complete electrification of the built environment. So every house will be electrified. There will be no fossil fuels in Ithaca by 2030. But with it comes an interesting conversation what that means on the embodied carbon side. And that's where we want to be involved in this conversation. And our solution to that is the construction of a digital twin of the entire city to then do scenario simulations and trade-off simulations of different strategies in this decarbonization efforts, really thinking decarbonization holistically, so embodied and operational carbon emissions together. This is a project that we're working together on with the Environmental Systems Lab and Professor Timur Dogan at Cornell. But it's also has NYSERDA as a partner, Siemens as a partner, Avangrid as a partner, to really understand these urban scale questions using Ithaca as a case study. And I'm not going to go into details of that model that we're setting up, but it's essentially fed by aerial LiDAR data that is publicly available, GIS data and footprint data that is publicly available, tax information that is publicly available. And we're using all of this and to generate, on the one hand side, a clean geometry, and we're mapping basically our construction archetypes to this geometry to then generate a model that can do both circularity analysis and energy plus simulation for all 6,000 buildings in Ithaca. And so naturally, we're starting with simple information like what kind of housing types do we have, what kind of heating systems do we have, right? So this is something that we can map very quickly. We're then going the next step. This is a simulation of that of the heating load for all buildings. That is basically the result of this energy plus simulation for all the buildings. And when we then combine that with, for example, a rooftop PV potential analysis of all these geometries, we're suddenly talking about an urban scale conversation. Can we, for example, fulfill all the load demand that we have through the electrification of these buildings with local PV, with the local PV potential based on a geometry analysis of the city? And the interesting thing is that if we bring it down through the electrification and a meaningful retrofit over the year, we can actually do that, right, on an urban scale. Naturally, of course, in January, we have a problem, and in July, we have a bit more energy than we need. But as a year budget, on average, we can cover the electricity demand through local generation. Our contribution is really on sort of the detailed understanding of the built environment in terms of materiality. This is a summary of sort of the urban material cadastre of Ithaca, how much timber is in these buildings, in which buildings do we have which intensity of materials, where is what kind of embodied carbon in there. But then when we now combine this, and these are slides that were generated yesterday because we finally got it to work just in time to show this to you, is an understanding of the circularity of these constructions. So now we did an energy blast simulation for all these materials, for all these buildings, but now we also did a material passport calculation and a circularity calculation for 6,000 buildings. And the interesting thing is that, of course, now we know which materials are where. We did that before, but now we also know what kind of circularity is attached to these buildings. Unfortunately, the scale is really hard to read, but we're ranging between 0 and 70% in these buildings. The yellow buildings are extremely circular. The bluish magenta ones are less circular, which doesn't necessarily surprise us, knowing the stock a little bit. This has to do with age and material use in these buildings. But the interesting thing is, if you now compare these numbers with, for example, understanding of what materials are in these buildings and how are they constructed, we're seeing in this case now only timber and the amount of timber in these buildings. And so now you can say, well, if I need timber, or if a building comes to the market or asks for a demo permit, you can look up, hey, this is actually not only a lot of timber in this building, it's also easy to get. Or in this case, there's a lot of material in here, but it's really hard to get. And so we have a much more informed conversation on the urban scale about circularity and materials. None of this works without policy. And so in 2020, we founded a stakeholder network called CROWD, which is short for Circularity, Reuse, and Zero Waste Development. And it's a local growing stakeholder network for New York State. We had really interesting partners join recently. For example, the Preservation Association of Central New York is one of the more recent members, but we also have the city of Ithaca, or now city of Troy, join CROWD. And the agency that we're creating with this is really to have a New York State partner that talks about policy in the built environment regarding circularity and deconstruction, and specifically reuse. And we've created a really interesting platform that is now at the point where we talk to the New York State Assembly, talk to certain senators. We're talking to 7 different cities and communities about policy changes towards reuse. And the outcomes of all of this is publicly available. So if you're interested, the most recent publication is a local government policy guide to alternatives to demolition through deconstruction and building material reuse. And all of this is available on crowd.org, crowd with a 0, not an O. Next to policy, we also need to talk about code. One of the things, for example, with timber is that, at least in New York State, you can't just go and reclaim timber in a structural application. It's not allowed. And so we've partnered with SBP here out of New York, and are in the midst of a really interesting test series that looks at reclaimed timber and sort of the steps that we need in updating our code to allow structural timber reuse. And that has to do with the questions, how do we even find out what timber that is? How do we classify that timber? What kind of informations do we need to know to have a meaningful structural engineering design? And how does that comply with code, and where do we need to make changes to the code? The example that you see on the screen is an interesting one. It's a screw test. Because we realized that we don't have any way to classify the re-screwing of a screw. So if you take a screw out of a connection and put that screw back in, we can't calculate that anymore. because the code says it needs to go into virgin timber. But if that hole is already cut, or if that screw is being reused, we can't ask for a building permit. And so here we're trying to just simply take the screw out, put the screw back in, do a destructive test and see what changes. And so this, it sounds very, very, very direct and immediate, but it's interesting to see where we need to start to facilitate reuse in the built environment. I think. Okay. The other stream that we're looking at is design for disassembly. So how do we design differently from now on? The example that I want to show is the Urban Mining and Recycling Unit, which is a building that we constructed in Switzerland with the office, together with the office of Werner Sobek. The building that we're actually looking at is the part in the middle of the screen with the copper frame. It's a unit within the so-called nest, which is this basically shelf-like structure that you're seeing around the Urban Mining Recycling Unit, which is a testing facility of the materials testing laboratories in Switzerland. And they came to us based on a book that we published in 2014, Building from Waste, where basically the question was, it's nice that you're writing about all these resources out of waste academically, but can you actually prove it? Can you actually use these materials in the built environment? And so we had our work cut out. As you see, it took 4 years to make it possible. But the claim was that we built a building where all materials that go into the building can return to their cycles at 100%, which is a very academic goal for a built project, and was maybe only possible in this specific setting where the empire actually gave us the time and maybe also the money to go the extra step to figure out how this is possible. Design for disassembly really is the guiding principle of this, which led in some parts to modular construction. So we delivered these units, 7 units that make up the whole unit. In one day. We basically rolled them into the building, only pinned them down on rail foundations. And so the idea is that at the end of life, we just roll them back out, bring them back to the factory and disassemble them. And the disassembly was always the guiding principle, as you can see in the drawing on the right, on really making sure that every connection is known, every material is separated in different life cycles in different locations. I want to show a couple of examples. How am I in time here? One question, for example, that we asked ourselves is, can you build a brick wall without mortar? Mortar, of course, being sort of the issue when you want to directly reuse the brick. So this is our answer to that, where we developed a new brick that has a tongue and groove system, and that has a post-tensioning cable system, where you're creating a structurally stable wall basically by tensioning these rods. If you want to reuse that brick, you basically unscrew that steel connection, take out the brick. You can use those bricks somewhere else. You can reshuffle the wall. You can do all sorts of things with it. The other question that we had, how can we build without any adhesives? So there's not a single type of adhesive in that building, no silicone, no glues. And it becomes especially interesting in wet rooms like the bathrooms or restrooms. And so the example you see here are the 2 different bathrooms the unit has, and we opted for the largest format of, in this case, glass or HDPE panels that are only pressed into dry gasket sealants. And so if we wanted to take these out, it's basically also 2 screw connections, and you can take the whole panel out. There's no silicone left on it. You don't have to scrape anything. These are basically as they were delivered from the manufacturer. You can take them out and reuse them somewhere else. The building has been standing since 2018 without any water leakage or damage. So it's possible to build without adhesives. Another question that we ran into, and to just show you sort of the level of detail that you need to go into if you want to get these last couple percentage out of a building, is that we didn't find a single faucet on the market that fulfilled our goal of a recyclability or reusability, because they're usually 3 different materials, pressure fit together, copper pipe in the middle, some movable parts out of plastic, some surface material around it. And they're not meant for disassembly. And so usually these things end up in the landfill. And so at the end, we decided we need to partner with someone and actually develop our own faucets. And so the faucets in this unit are 3D printed stainless steel, where all parts, the pipe, the movable element, and the faucet itself are printed in one go and in one material. So there's a monomaterial solution. And if you can't reuse it for the 10th time anymore, which is, of course, the hope that you first do that, then you can reprint something else out of that material without any loss. Documentation is key. So that unit has its own material library with all the 24 materials that were used in that material. That's online available. That's also as a physical sample in the unit to sort of store that memory. And in the end, we used the unit to create a material passport. At that time, Madaster was the leading sort of agency that allowed to do that. By now, we have a couple more. Madaster is still the leading agency in Europe, at least. Madaster is short for Material Cadastre. And it allows us to know which material is where in the building, how is it connected, what dimensions do we have. So to basically foresee a future deconstruction and assuming that we're not part of it. And so how much information do we need to pass on to someone else who wants to then reuse these materials in their own buildings? Going back, one more project from Ithaca with the same intention behind it. The wood that we took out of the deconstruction project that I showed you earlier, part of this was used as a student project in a design for reuse studio. And the idea was to build a structure on the art squad for the Cornell Biennial that is built entirely out of reused materials, that is designed for disassembly. So the result of that is called circulating matters. And it's a curious little staircase that deals with sort of the multiple types of circulation of materials of humans, but it's large enough to need a building permit. And so we needed to go through the whole process with the city of Ithaca on structural timber reuse and how would we need to be permitting that. And so this is the first structural timber reuse in Ithaca that has a building permit and sort of creates a little bit of a precedent, but for us more creates an understanding of the steps that it takes for a process like that. And of course, it deals with the many qualities, the sort of the aesthetics that come with material reuse, the play between the old and the new, or the cut and the surfaces of the old. It teaches students how to deal with these materials. But more importantly, it asks the question similar to the Mehrwert Pavilion, how we design with a non-standardized stock. And so the details that we needed to develop had to deal with a tolerance of almost ½ an inch, because these materials were, of course, partially hand cut or pre-industrialist cut, 120 years old, these beams that we took out of this building. And so we couldn't really have a standard connection detail because the tolerances were way too big. And so that's where in the end, the design of these beams that shoot past each other started, because that way you only need one surface that is sort of your defining dimension and everything else is free and can play with that. On the left side, you see a system sort of to start material passporting and documenting these materials and making the connection between the physical and the digital to figure out where was this in the building before, where is it now, and where can it go next. And the next in this case is now an installation at Art Omai. We just moved this structure a month ago into the Architecture and Sculpture Park near Ghent, here in upstate New York. So if you ever have the chance to visit this fantastic park, maybe stop by this structure. Is going to be there for the next couple of years. And it was a really interesting exercise because for a new location, of course, we wanted to update the design. We wanted to reshuffle the design slightly to talk about the new site conditions, and the design for disassembly really allowed for that. And we were able to reuse all of the materials. I want to finish with a little software application that we're working on, driven by an understanding that was derived from the Urban Mining and Recycling Unit. I showed you this material passport, and we were always annoyed with ourselves, essentially, that we did that way too late, right? We first built the building, we designed the building. In the end, we had a nice BIM model. The BIM model gave us all the information that we needed to then calculate the circularity of the material and publish this material report. Now that's too late if you want to use all that information as a design input, right? And so not only in academia, but also in the industry, we were trying to find a tool that allows us circularity calculations at an early design stage where it is most impactful, or at a deconstruction stage where it is most impactful. Because the moment you have, I don't know, a construction documentation done, all the major decisions are done, right? You have materials already procured. You can't make changes because that's really expensive. So we need to have these conversations much earlier. But at that point in time, you usually don't have enough information to generate traditional material passports because they're based on exact material classifications or exact dimensions, et cetera, et cetera. And so Rhino Circular is a free application. You can go and download that at Food for Rhino if you're working with Rhino as a design tool. That now allows that. This is the material and building circularity report that it spits out for the little staircase that you just saw earlier. But it essentially works at any design stage. It links our construction archetype library with specific geometric information, and it constantly updates, right? So if you make a design change, or if you change the material link, you always have an immediate feedback on the circularity of your design. And you see that basically in your drawing environment. And so it's omnipresent. If you want it there, you can of course turn it off, but if you wanted to, it's omnipresent. And we're pushing on Monday, we're pushing a new version to Food for Rhino that now also allows to visualize circularity in the geometry. So your geometry itself gets color-coded by the circularity indicators. And so you can, of course, decide on your own color scheme. But in this case, the magenta parts are really high in circularity and the yellow ones are problematic. And so it's not just an abstract number now where you say, well, somewhere in your skin you have a problem, but you now see, hey, this piece has a low circularity rating. And so you can go in and say, well, let's change that. Right? Let's change the design of that. And if you need any more information, I'm happy to take questions. But as mentioned by Andreas, we've had a couple of publications in the past. The most recent that is out is Building Better, Less Different, Circular Construction and Circular Economy. But that book is part of a series, and the next one is coming out in October, so next month, which has the theme Clean Energy Transition and Digital Transformation. And so this is a little outlook to that. Thank you.
Thanks so much, Felix. I have a million questions, but for the first one, I was curious about what goes into creating the rating for circularity. Like, which components are you considering for giving that rating 0 to 100?
Yeah, I mean, that's a really good question. We're using a mathematical formula that was published by the Ellen MacArthur Foundation for now. knowing that it is incomplete, but it essentially looks at the production of those materials and everything that goes into the production of the material, as well as the end of life scenarios, and knowing how different these scenarios are from one location to the next. There's already the first problem in these assumptions, because this is now based on industry standard EPD information that we have for the United States. In a future scenario, I'm hoping that we can get much more local in these data sets, but they are simply not available yet. And so we're working on them, and we're looking for partners to, for example, develop specific data sets for specific locations or specific products, to then in the software be able to say, where is my building located, and automatically select the most suitable data set to run these calculations. But for now, we're really looking at basically material flows and pathways from the very beginning to the very end of the life cycle of the material.